My name is Aditya Joglekar. My registration number is 19BCT 0223. Today I'll be going to talk about time complexity. So what do you mean by time complexity? Well, time complexity simply means that it's an algorithm which signifies the total time required by the program to run it till its completion. Well, time complexity is nothing but it measures how long a program function takes to process a given input. We give an input, it processes, it gives an output, the duration is time complexity, very simple. Now we move on to, there are few types of time complexities. So these examples are constant time complexity, denoted by big O of 1, linear time complexity, big O of n, logarithmic time complexity, big O of log n, quadratic time complexity, big O of n square, and exponential time complexity, big O of 2 to the power n. Now we come to the next stage, which is also one of the most important stages. Here, we must note that since the algorithm performance may vary with different types of input data, hence for an algorithm, we usually use the worst case times complexity of an algorithm because that is the maximum time taken for an input size. Now, how do we actually calculate time complexity? Well, to calculate time complexity, it is quite complex, but I'll try to explain it in a very simple way. Now, the most common metric for calculating time complexity is big O notation. This removes all constant factors so that the running time can be estimated in relation to n as n approaches infinity. In general, you can think as you have time complexity equals to a n plus b, where a is the coefficient relation with n and b is any constant. So we take n. First, we should always choose the fastest growing set. So imagine we have n square n plus c. Now we have two to choose from. One is this, one is this. So what will we do? We choose the fastest growing set. Here between n square and n, the fastest growing is definitely the n square. So we choose n square, we remove this, and we of course remove this one. And after choosing, we have a n square. Now what we do is remove the coefficient in relation with n. Now what you have is big O of n square. It's very simple. Now for the next, we will first take linear time complexity. Linear time complexity is as what it sounds. The running time increases at most linearly with the size of the input. Linear time is the best possible time complexity in situations where the algorithm has to sequentially read its entire input. Basically what it means is we give an input and it gives an execution. It has an execution time. Now if we increase the input, see in this graph you can see y, x has the input and y has the execution time, which is more in microsecond. Now this execution time increases linearly. This is why it's called linear time complexity. Now we check the expression. Expression is t equals to a n plus b. Now as we state by the big O notation method, we cancel the a, we take the n and simply put big O in front of it. So we have big O of n. This is linear time complexity. Here for an example, we have a for loop. For this for loop, we have I equals to 0, I less than n, I plus plus, which is incrementing. Now we have a general statement here. Now for the single for loop, we can say that the time complexity of the algorithm will be always linear, which is again O big O of n. We can say that when n doubles, so the running time also doubles, hence the linear graph. Now for the next one, constant time complexity. Well, an algorithm is said to be constant time if the value of Tn is bounded by a value that does not depend on the size of the input. For example, if we take any single element in an array which takes constant time as only one operation has to be performed. Now, whatever the input may be, whatever the input size may be, always the execute time will be same. It will be constant. So t equals to e. Well, we have nothing here. It is constant. We don't have any n because it does not have any relationship with n. So what we have, we can rewrite e as e multiplied by 1. Now, what we say is e multiplied by 1. Now we have 1 e. We take out the e. We have big O of 1. Now, it's for a single statement. We can say it has constant because there is no relation with n. Now we can see an example here for this code. We have the constant. So given integer 5, it is all. It gives an execution time 2.4. Now again we run it given even integer and here get 4 is even. So we see that this is an example for constant time complexity. Now for the next one, we have quadratic time complexity. For this quadratic time complexity, we see that the graph is between time and input n, data input n, and after some time, well, it will not increase. It's almost same here and increased a little bit here, and after this point, it increases sharply. So this is what a quadratic function, and what we call it quadratic time complexity. So its expression is as t equals to an square plus bn plus e. Now with the big O notation method, we have 2 here, but we choose only the fastest set, which is the n square. We cancel out this. We have an square. Now we take out the coefficient a. We have big O of n square. Now, for example, we have a nested for loop. Yes, a nested for loop is used for quadratic. Now, we have a nested for loop, so this will always be a quadratic since when n doubles, the runtime increases by n cross n. We can also see an example of this one. So this is just sum of diagonals of matrix. We'll run it. Now let's give it a 3 cross 3 matrix. Okay. Coefficient, random coefficients. So we'll give it. So we have this matrix. Sum of main diagonal is 11. Sum of off diagonal is 10. And it executed without any effort. So what we have here is same nested for loop, and it will return the output, and it will be under quadratic time complexity. Now we also have logarithmic time complexity. It is simple in the form of log form, and same execution time versus input. We have t equals to a log n plus c, cancel c, cancel a. We have log n, big O of log n, very simple. Now, for example, we have this while loop and if and else. Now, this algorithm will be logarithmic time complexity. The running time of the logarithmic is proportional to the number of times n can be divided by 2. This is important. Now, if we compare the two graphs, linear and constant time complexity, what can we conclude? Basically, we can conclude here is for any input, the execution time is constant, which is this. And if we increase the input, the execution time increases. So for example, take any input, large input. Here example, it will have the same execution time, and we take the same number of input here, but the execution time is very large compared to the constant one. So here we can say that this is better performing than this. Also, we should understand that it also depends heavily on the system. If we have a nice high performing system, it will always give low time, which is better. Low time. And if we have an old PC and a system which is not high performing, it will have more high executing time, which will take more time to execute the program. So we also have a number of different complexities, time complexities, such as O, big O expression, and we can take big O expression. It is the set of function that grows slower than or at the same rate as the expression, which we take always in the worst case. Now, as I already said, worst case is the best way to check any program, whether it's functioning or not, but we also take different best and average. So we see omega, it is set of function that grows faster than or at the same rate of expression. The big O was grows lower than or same. This is faster than or same rate. It is omega. It is considered in best case. And the remaining is theta, which you can probably guess it's for the average case. It consists of all functions that lie between both O and omega. Now we have already seen the codes running, different codes for constant one, and we have linear and we have quadratic. So let's go to solved example. I have few solved examples here, which helps us to determine whether if the code is of which complexity. So we'll start example 1. Example 1 is for loop I equals to 0, I less than n, I plus plus statement, and it will give for the execution time n. We take n. So big O of n, simple, straightforward, linear complexity, big O of. Now this is if we increment from 0 to 10, we go up. It is linear. It adds the array we are adding in the given array, which is basically from 0 to 10 or any numbers. And similarly, we take I minus minus, which is decrementing, which means it is going from 10 to 0. But if we see 0 to 10 or 0 to 10 to 0, it performs in the same number of steps. Step numbers are same. So here also we will get linear complexity. Nothing different. Both are same. So next example, we have I equals to 1, I less than n, I is I plus 2. So for each I plus increment by 2, we have n divided by 2. Function is n divided by 2, but since we take out the constant out, we are left with it is of the order 1, and we have O big O of n. Now we take this example. Let's see. For I equals to 0, I less than n, and I plus plus nested for loop. Here we see. Now we can already imagine what this will be. Yes, it will be O n square. But how does it come? Let me show you. For j equals to 0, j less than I. These are the conditions I put. Now, for the statement, Now since I, we have made 3 columns, 1I, 1j, number of time it is executed. Now we have I equals to 0, so start with 0. Then we have a condition which is j should be less than I, but we can't have less than 0, so it does not execute. Execution 0. Second one is increment. We increment the number I plus plus. We have plus 1 here. 1 less than 1 is 0. We take 1, it does not come because it does not satisfy this condition. Execution number of time 1. Now again plus 1, we get 2. We have 0, 1, 2, but 2 will not get executed, only 0 and 1. So we have 2, and this goes on till n times. And for n, I equals to n, we get number of execution n. Now the total time of the function executed is adding those. So 1 plus 2, 3 up to n. So this is just sum of n natural number, which can be rewritten as n into n plus 1 by 2, which also comes to be n square plus 1 by 2, which comes to be, which we can write it as 0 big O of n square. Now another example we have p equals to 0 for I equals to 1, p less than equals to n, I plus plus, and condition is p equals to p plus I. So write it 1, 2, 3 plus 1, again plus 1 up to k times. Now we have p is what? P plus I. P is also less than equals to n. Just p is basically 0. We kept 0. 1. 1 plus 2, 3. 1 plus 2 plus 3, 1 plus 6. Up to 1 plus 2 plus 3 goes to k times. Now, it's similar situation as this. This is up to n times. This is up to k times. Now, the given condition is p is less than equals to n. Now, what will happen if p is greater than n? The execution stops because the condition is not met and it stops. So if we assume it and put p equals to k into k plus 1 by 2, then after substituting here, we get k plus k plus 1 by 2 is greater than n, and then we'll go here. After solving it, we get k square greater than n, and what this is very important result, we get k is greater than root n, which means k is equals to root n. So if we get, so which means that if we get till root n, the execution stops. The execution stops. So you can write it as, so the time complexity will be equals to big O of root n. Now another example we have for loop I1, I less than n, I equals to I into 2. The statement here, n. Okay. Now we take I. Again we take I equals to 1. Then this is the condition. 1 into 2, 2, 2 into 2, 4, 4 into 2, 8, and this is the pattern which goes on and on, and finally we have 2 raised to the power k. Now if we assume, see here it is I less than n. If we assume if I is greater than equals to n, then I equals to 2 to the power k we substituted. Here if this condition is met, it stops. So we try to do it. I equals to 2k, 2 to the power k greater equals to n, and n value is log n to base 2. So we can write Pc equals to big O of log n to the base 2. And one last example I'm going to take today. So this for loop I equals to n, I greater than 1, I equals to I divided by 2. We have a statement here and comment. And since I equals to I divided by 2, we take I, and I is n. Since I equals to n, we take I n, and increment it, we get n by 2, again n by 2. So to n by 2 to the power 2, n by 2 to the power 3 goes on till n by 2 to the power k. Now we have condition I greater than equals to 1, and if we get I less than equals to 1, program stops. So therefore we substitute it, we get n by 2 to the power k less than 1, and similarly after solving we get n log 2 to the base log n to the base 2 equals to k. So the time complexity here will be equals to big O of log n to the base 2. Both of them are similar, but approach is very different. Now this for today. I hope that I was able to convey something to you, and thank you.